Welcome again to Physics 142 Online. Today I'd like to give an introduction to the physics of a special kind of traveling wave phenomenon, and that is standing waves. As we'll see in a minute, standing waves occur when two traveling waves with exactly the same wavelength and frequency travel in opposite directions through the same medium. And to understand why we call them standing waves and what's really happening, we first begin with the principle of superposition. The principle of superposition is based on the observation that when two or more waves pass through the same medium at the same time, the net wave disturbance is just the sum of the two individual waves. So you can see here that the two pulses traveling in opposite directions that have the same shape meet in the middle, and the net disturbance is the sum of the two, and then they continue on in the same direction they were initially traveling. And the interesting observation here is, as I said, the net displacement is the sum of the two individual displacements, and that when these waves pass through each other and emerge on the other side, they do not affect the shape or the direction that one another was traveling. So mathematically, we can see that the net wave disturbance for the simple case of a one-dimensional problem, this could be one-dimensional waves on a string, the net wave disturbance is the sum of the two individual waves. And then the other observation, as I said, was that these two waves, even though they move through the same space at the same time, they don't change directions and they don't change their shape. And that's quite interesting. It doesn't always happen. There are many cases that we could talk about where the principle of superposition does not hold, particularly if the waves have large enough amplitude that they do some sort of permanent deformation to the medium. But for relatively small amplitude waves traveling through a medium such that the properties of the medium don't change, the principle of superposition generally holds. So, that's what I asserted. I asserted a minute ago that when you have two traveling waves in opposite directions, that they produce a standing wave. So let's see how that happens. These two waves are identical in amplitude and in wavelength, which is given by the k value, the wave number value, and in frequency. So the only difference is the sign, which then relates to the direction of motion. Y sub 1 is moving in the negative x direction, y sub 2 in the positive x direction. So according to the principle of superposition, when we add them together, we simply get the net displacement, the net disturbance. So you can pull out a factor of a from the two, and to make further simplification, we have to use a trigonometric identity that you may remember from previous courses. There's a similar kind of identity for the sum of two different cosines, the cosine of two different angles, but the one that we want is the sum of the sines of two different angles. And taking this expression and substituting it into the net displacement for our two oppositely traveling waves gives us this result. So the net disturbance has an interesting property that the individual x and t values that go into telling us what the net wave disturbance is, they're separated. One of them is in the argument of the sine function, the other is in the argument of the cosine function. And as a result, this wave is special. The equation of a standing wave is special because it does not travel in time. In other words, the positions of the peaks and the troughs do not move to the left or to the right. They stay in the same place. So if we look at the first term, we see that it only depends on position, sine of kx. The cosine omega t term only depends on time. So that if we pick a fixed point in space, some value of x, like 2 meters, then we can look at the displacement of the medium at 2 meters as a function of time. And the sine term will be a constant because we've chosen a particular value of x, and all that we'll see is that the point oscillates the way that a simple harmonic oscillator would, with an amplitude equal to 2a times the sine of that argument. So the amplitude changes from point to point. As we move to different values of x, the amplitude changes, but the time dependence is given just by this cosine function. So if we want to answer the question, what is the maximum amplitude of a standing wave, then we would take the expression, the general expression for a particular point on the wave, and this realize that the term out in front of the cosine function is the amplitude. So where that would be a maximum would be when the sine value is equal to plus or minus 1, because what we really mean is when is the amplitude greatest, either in the positive or in the negative direction. So for the sine to be equal to plus or minus 1, that tells us the values that the argument has to have. So of course, the kx can either be pi over 2, because the sine of pi over 2 is 1, or it could be 3 pi over 2, because the sine of 3 pi over 2 is negative 1, and so on and so forth. So we generate a series of values of kx. K, remember, is 2 pi over the wavelength. So for a particular wave, k is fixed, and what this tells us is the value of x that we can actually determine corresponding to these positions of maximum amplitude. Some compact notation that we can use is to write kx equals n plus a half times pi, where n is just a non-negative integer, because this equation will generate all of the values that we got above. These kinds of points, the ones that have maximum amplitude, the peaks and the troughs, are referred to as antinodes on a standing wave. And if we substitute in for k equals 2 pi over the wavelength, then we can solve for x. So we've taken this k value, plugged it into the equation above, which gives us this relationship right here, and then simply multiply by lambda over 2 pi to solve for x. And that tells us, again, the positions along the string in the medium where the amplitude is a maximum. And we'll use this in some of the homework problems that you'll have to do during this section. We can do the same thing for points of minimum amplitude. All right? What values of x will be the points where there are nodes? Nodes being positions of 0 amplitude or 0 displacement. So for that to take place, the sine of kx will have to be 0. And we can easily figure out the values of kx that satisfy that equation. Kx equals 0 works, kx equals pi works because the sine of pi is 0, and so on for 2 pi, 3 pi, 4 pi. Any integer multiple of pi, non-negative integer multiple of pi, satisfies this equation. So we can write kx equals n pi, where n is a non-negative integer, and as I said, these kinds of points with 0 amplitude are called nodes. They are the points that are fixed, that do not appear to move at all on a standing wave. So substituting in, once again, the value k equals 2 pi over lambda up here gives us this relationship, and then solving for x, we get n lambda over 2. So for n equals 0, 1, and 2, and so on, we get the values of x that correspond to the positions of the nodes. The grand finale here, the summary of everything that we've talked about with regard to standing waves, is that there are regular positions for both the nodes and the antinodes, that these occur in predictable places along the string or in the medium. And if we know the wavelength, then we can calculate these points. And these formulas are very useful, but probably even more useful is a graphical representation of what the standing wave looks like. And so if this was all very abstract, hopefully the picture that you see right now will help explain it more clearly. Imagine that this is a string that's being shaken perhaps at one end, and so then there's a wave traveling down, and then another wave coming back from the left to the right, and those two waves produce this standing wave pattern. And the blue wave shape shows where the string would be at any particular point in time, when it's got its maximum displacement, and then when it's flipped over in the other direction, where the amplitude has become, where the displacement has become negative. And each of these peaks oscillates back and forth between the two extremes, much the way that a simple harmonic oscillator, a mass connected to a spring, would oscillate back and forth between two extreme points. So the red arrows represent the oscillations of points on the string, and you'll see at the left end there's a node, right here there's a node, another half a wavelength there's a node, and so on. The positions of the nodes are the places where the sign of kx is 0, and the positions of the antinodes, whether that's a peak or whether that's a trough, doesn't matter, those are the places where the sign of kx is actually plus or minus 1. That equation should say plus or minus 1. What's important in this diagram then is that it shows us, instead of having to remember the formula that was on the previous slide, these formulas down here, we can see that if there's a node at x equals 0, the first antinode will be at lambda over 4, and the next antinode will be at 3 lambda over 4. And so if we go back one just to check that out, sure enough, antinodes occur at lambda over 4, 3 lambda over 4, 5 lambda over 4. So we can see how that's shown right here. How do I know that that's lambda over 4? Well, remember, one complete cycle of the wave is one wavelength. So if the left-hand edge of the string is x equals 0, then x equals lambda over 4, lambda over 2, 3 lambda over 4, and finally lambda. So that allows us to see where these special points are for the standing wave. And this picture is probably more important to remember than the equations on the previous page, because if you can remember the picture, then you get the locations of the nodes and the antinodes for free. You can just realize what the wavelength is and write down the x value of each of these special points. All right, here's an example that shows how to apply what we've learned to a case where there's actually some numerical values. A standing wave results from the sum of two transverse traveling waves given by these two equations. And you'll see that the amplitudes are the same, and the argument of the sine function is the same except for the plus and the minus sign. And it tells us that x and y are in meters and t is in seconds. So the question is, what is the smallest positive non-zero value of x that corresponds to a node? And so now let's work this out using the equations and the plot, the diagram that we've just learned. So for this example problem, we're trying to find, again, the smallest positive non-zero value of x that corresponds to a node. And why non-zero value of x? Well, usually in a problem like this, we assume that the string begins, its left edge is at x equals 0. So negative values of x don't really make any sense. So what do we need to do here first? Well, following the prescription that we've learned in the notes before, we want the net disturbance y, and we know that that's equal to y1 plus y2 of x and t, and we'll write these down and then realize that we already know how to add them together. So again, these have the same values of a and k and omega, and I'm going to use those symbols here because it will enable me to avoid having to write down so many numbers all at once. So the two have the same amplitude, they have the same k and omega, and so they only differ in the plus or the minus sign in the argument. One's traveling in the positive direction, the other in the negative direction. So we already know that what this gives us when we use that trig function is 2 times an expression that has a cosine and a sine function. And the first term is the sine of kx, and the second term is the cosine of omega t. And sometimes we'll put those parentheses in, and sometimes we might not, but they're always understood. If you see sine kx without the parentheses, it's the sine of the product k and x. So once again, what this gives is 2a, right, times sine kx cosine omega t. And so what that means is you've got the amplitude function here, right, that multiplies the cosine omega t term, and what we have is a position-dependent amplitude for this standing wave. That's what happens in a standing wave. So where is the smallest positive non-zero value of x that corresponds to a node? Well, just remember, node means that y is equal to 0 at certain values of x. And there's a whole series of them. We want x min as long as it's greater than 0, non-negative value, or perhaps equal to 0. We'll see. All right. So for y equal to 0, well, the cosine omega t term goes back and forth from +1 to -1 in time. So we can only be sure that y will be 0 at a particular value of x if the amplitude function goes to 0. So that means we want 2a sine kx equals 0, right? Which means that the sine of kx equals 0, and in turn that means that kx can be 0, right? It can be what would be the next value? It would be pi, right? 2 pi, and so on. Any integer multiple of pi. So we're trying to solve for x. Remember, k, the definition of the wave number k is 2 pi over lambda, and substituting that into the expression over here means that 2 pi over lambda x is equal to 0, pi, 2 pi, and so on, so that if I solve for x, I get x equals, well, the first term will be 0. I'm going to multiply both sides by lambda over 2 pi, 0. And if I multiply lambda over 2 pi, I'll get lambda over 2, right? Lambda over 2 pi. The next one will be lambda, and so on and so forth. So if I know the value of lambda, then I can find the value of x. Oh, and by the way, we want the minimum x that's non-zero. So x equals 0 will be the minimum value of x, but we don't want to use that one. And so here's the one that we want. That's the minimum value. So what's the wavelength? Well, we just have to go back to our expression to find the wavelength. So k equals 2 pi in the equation, right? Because it's the sine of k times x. So that means that the wavelength of 2 pi over k, well, that's just 1 meter, because it says that all the distances up here are in meters. So lambda is 1 meter, therefore x min for a node is equal to 1 meter over 2, or 1/2 meter for a node. And so I think we've solved the problem. We found the location of the first node, the one at the smallest value of x that's non-zero. Well, now we know that standing waves occur when you have two waves traveling in opposite directions in the same medium that are identical in amplitude, wavelength, and frequency. But how would you actually set that up? And a simple way to do it is the way it's done on stringed instruments. And that is to have a string that's stretched and under a certain tension, and to pluck that string in the middle. What does the plucking do? Well, you pluck it somewhere in the middle, and that actually generates two waves, one traveling to the left and one traveling to the right. The two ends of the string, which are usually fixed, then act as reflectors, because the wave that comes in from the right to the left hits the end that's fixed and it gets reflected back. And the same thing happens at the right end. The wave traveling from left to right hits the right end and reflects back. And now the two reflected waves, which again are identical in amplitude, wavelength, and frequency, they obey the superposition principle, and they add together on the string to form a standing wave. In class, I'll be able to show you some visual examples of how we set this up using a vibrating string. But here, what we'd like to do is show the special conditions that these kind of standing waves have to obey, because it turns out that not just any wave will be generated when you pluck a string like this. The waves will have certain very special frequencies that depend on the length of the string and what it's made out of. And that's why one stringed instrument differs from another one. So what do? First of all, we can see that if the string is fixed, which means motionless at both ends, if somehow that string runs over a wooden piece that holds it and keeps it from vibrating, then the boundary condition for this string is that the both ends have to be nodes. There can't be any motion of the string at the ends. And that boundary condition is what imposes the requirements that we can use to figure out the frequencies of the standing waves that are set up. It's really quite easy. So if we know that both ends of the string have to be nodes, then at any point in time the maximum displacement of the string will occur in a wave pattern that looks like this. The two ends are nodes, and the longest wavelength, and that means the shortest frequency that can occur on that kind of a string, is where the two nodes have one antinode in between them. And of course that antinode will flop back and forth from positive to negative, and when we look at something like this, if we actually can see it, we'll see something that looks like this looped pattern, where the positive and the negative loops show the locations of the antinodes. So this pattern on a string is referred to, for reasons that will become really clear in a few minutes, as the first harmonic frequency. It's also sometimes called the fundamental frequency of the string. Right away what we can see is that if the string has a length L, then the length of the string is half a wavelength. And this loop, whenever you see one of these loops, the distance from one node to another node, remember, that's not a wavelength, that's a half a wavelength. That'll be easier to see once we have a little bit more complicated pattern. But just think of a sine wave. The distance between the zero values on a sine wave is not the full wavelength, but only half the wavelength. So if L is half a wavelength, then the wavelength is 2L, and the speed, we go back to our equation for the speed of a wave on a string. If we know the tension, and if we know the linear mass density, the square root of that ratio is the speed. We're trying to calculate frequency. So frequency times wavelength is speed. Frequency, therefore, is speed divided by wavelength. And this first frequency, called the first harmonic frequency, for the simplest pattern that we can have, we'll label F1. So since V is F lambda, then that means V equals F1 times the wavelength of 2L. Solving for F1, we get 1 over 2L square root of F over mu. And as I said before, these frequencies, the frequencies of these standing waves, depend on the length of the string. They also depend on what the string is made out of, which determines its linear mass density, and of course the tension that we keep the string at. And so when you tune a stringed instrument like a guitar, the way you tune it to get it to match a certain frequency is to change the tension. Obviously, once you have the string, you can't change the mass per unit length, and you can't very well change its length Well, unless you do something that musicians know as fretting the string. Then you effectively change the length. But without doing that, the length is fixed, the mass per unit length is fixed, all we can change is the tension. So that's how we adjust stringed instruments to match a particular desired frequency, which is what tuning is all about. Well, let's look at the next more complicated wave pattern, which still has to have nodes at the ends, but now this will introduce one additional node halfway in between the two ends, right at the middle. And here is the second harmonic pattern, or the second harmonic frequency. As I said, nodes at the ends and one in the middle. So you see now two loops, and here it's pretty clear that while one loop from node to node is half a wavelength, between two loops you have an entire wavelength. And so the length of the string is L, which is now the wavelength. Going through the same analysis very quickly, we know the speed. The frequency, we'll call it F2. So velocity is frequency times wavelength. The difference here is that the wavelength is L. And now F2, 1 over L, square root of F over mu. Why do we call it F2? Obviously it's the second pattern, but we also call it F2 because if we compare it to F1, the first harmonic frequency, it's a multiple of 2 times F1. F1 simply had a factor of 2 in the denominator, so that F2 is twice F1. F1 is called the first harmonic, F2 is called the second harmonic. It's a multiple of 2 times the first, and sure enough, there's a third harmonic. Each time we go to the next higher harmonic, we introduce one more node into the pattern. So there are nodes at the ends because of the boundary conditions, and now we have two equally spaced nodes in between the two end nodes. This means that these three loops from one end to the other, that marks out 1.5 wavelengths. So 3/2 of a wavelength is equal to the length of the string, lambda 2L over 3, and going through the exact same analysis we get, and of course this should say F3, that's a typo on my part. F3 is 3 over 2L times square root of F over mu, and once again by comparison, this F sub 3 is 3 times the first harmonic frequency. So we can keep on doing this over and over again to generate the whole harmonic series of frequencies. What do these mean again? Well, when we pluck a guitar string, depending on how hard we pluck it and exactly where we pluck it, we will get mixtures of these different harmonic frequencies. We won't just get necessarily one of them, although often one of them is the dominant frequency. But we will get a mixture of them. And so knowing what those frequencies are is important to being able to figure out the vibrational properties of a stretched string. So I think at this point I'll stop and save some examples for class time. But I hope that this gives you an introduction to standing waves, the mathematical properties, how a standing wave is generated, and what the basic frequencies are, the harmonic frequencies, which correspond to the standing waves on a string. So this has relevance in musical instruments, and we'll see some examples of how to use this in class.